All right. Thousands and thousands of years ago, when mathematicians or just regular people were looking at this square root of -1, because there is no real number, in the real number system, a number times itself, that can equal -1, we used to think, oh, there's no solution, okay? So for many thousands of years, the answer to this, mathematicians said there was no solution. There is no real number times itself when you have an even index that gives you this odd result. Even index means, in this case, a square root, and so a number times itself 2 times, right? So we can't get this solution. But many years later, still thousands of years ago, another mathematician said any quadratic, in fact, any polynomial, has roots, zeros, solutions, where there is a value x when y equals 0. So we've been solving this entire chapter. When y equals 0, what are my roots? What are my zeros? What are my solutions? So for example, what about this problem? If I graphed this, notice it's going to be touching up here at 1, and it's going to be the graph of a positive upwards facing parabola. Notice that it does not touch the x-axis, so there are no real roots. But there are still 2 values for x when y equals 0. These roots, though they're not real, we needed a way to express those. So if I solved this equation and subtracted 1 from both sides, I'd get x squared equals -1. And then if I rooted both sides, I got that x was equal to the square root of -1. So mathematicians were posed with this problem of how do I represent this result, this non-real root? How can I talk about this? So of course, mathematicians love to make up weird things, and so they made up imaginary letter I. So I is equal to the square root of -1. I stands for the imaginary root or number of the value square root of -1. Now there's a couple of definitions here that go with this. For example, I squared. I want you to imagine if I multiplied this by itself, the square root of -1 times the square root of -1, or I times I, and the square root of -1 squared, anything square rooted that is squared is just -1. So by definition, I squared equals -1. What about I to the third? I to the third could be rewritten as I squared times I. Well, we know that I squared by definition equals -1 times I, and so I to the third equals -I. What about I to the fourth? I to the fourth could be rewritten as I squared times I squared, and we know that I squared is -1 times another I squared, which is another -1. Well, what is -1 times -1? That's just +1. So I to the fourth equals +1. Well, what happens after this when we get to I to the fifth and beyond is it starts repeating again. So I to the fifth is just going to go back up here to this one. Well, why is that? Because I to the fifth could be rewritten as I to the fourth times a plain I. We know that by definition, I to the fourth equals 1. 1 times I just equals I. It brings us back up to this top row. So when we're trying to simplify just the imaginary letter I, some people just do a counting method where they go through these. So let's do a couple of examples so you can see what I mean. Let's do example 1. And example 2, and these are like what you're going to have on the quiz. I to the 6th equals, and I to the 17th equals. So we can break up these imaginary letter i's. I to the 6th could be broken up into I to the 4th times I squared. Why did I break it up into those? Because we have the definition of those already. So I to the 4th is known as just 1. I squared is known as -1. So the result of I to the 6th is just -1. Now, what do I mean by people counting it? I mean 1, 2, 3, 4, 5, 6. The answer should be -1, and it is. Let's go try I to the 17th. How many I to the 4ths can we squeeze into that? Well, I to the 4th, I to the 4th, I to the 4th, I to the 4th. If I add those all up using the add rule, then that adds up to 16. So we need one more to make I to the 17th. Well, we know that these I to the 4ths all just equal 1 times I. So my result here of 1 times 1 times 1 times 1 times I is just I. What if I wanted to do the counting method? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 17, back right up here to I. So if you want to just count it, or if you want to break it up, you're looking for the result to simplify. I to the 17th is just I. I to the 6th is just -1. I'd like you to try 2 of these examples on your own where you pause this video and try it and then play the video and make sure you got it right. So take a second to write this down. I to the 9th and I to the 19th. Take a second to break it apart or go do the counting method, and what would you get as your result? Okay, let's see how you did. I to the 9th can be broken down as I to the 4th times I to the 4th times one more I. 4 plus 4 is 8 plus 1 is 9. We know that I to the 4th is just 1, and then times I. 1 times 1 times I should just be I. I to the 19th can be broken down as I to the 4th, I to the 4th, I to the 4th, I to the 4th, that's 16, and then we need 3 more, 16, 17, 18, 19, to make 19. So we know that I to the 4th is just equal to 1, and that I to the 3rd, by definition, is equal to -I. So 1 times 1 times 1 times 1 times -I. My result here is just -I. So I to the 6th equaled -1. I to the 17th equals 1. I to the 9th equals I to the 19th equals -I. What if on these two you wanted to do it as counting to the 9th? You'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. The answer is just I. What about 19? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. The answer should be -I, and it is. How'd you do? There's going to be 2 of those on the quiz. All right, now let's go take a quick peek at the other types of problems we're going to use I on. Sometimes we're going to be given the square root of a perfect square, but there's going to be a negative with it. Now that we know about this imaginary letter I, when we simplify this radical, we're going to break it up into the positive square root and the root of -1, because by definition, we now know that this equals I. So the square root of 4 is just plus or minus 2. The square root of -1 is just I. That's my result. What is the square root of -4? Plus or minus 2I. Let's go do the next one. Break this up into the positive square root of 100 times root -1. We know that the square root of this is plus or minus 10 times this new imaginary I. Go ahead and write these next ones down and then pause the video and try them on their own. They're just like the quiz, just like the ones we just did above. Let's see how you do. So example 7 is a square root of -49, and example 8 is the square root of -121. Pause the video and go try these. All right, how'd you do? Did you get to break this up accordingly? And did you get plus or minus 7 root I? Did you break this up accordingly? And did you get plus or minus 11I? Excellent. All right. What if it's not a perfect square? If it's not a perfect square, like the square root of negative 24 or the square root of negative 75, then we're going to simplify the radical using the steps that we have learned before, plus this new imaginary concept. So the square root of 24 can be broken up into the root 6, root 4, and now square root of negative 1. Negative 75 breaks up into 25 times 3. Don't forget about the negative 1. Square root of 6 can't do anything, but the square root of 4 is 2. Square root of negative 1 is I, and then we leave the root 6 at the back. Notice that there are some things that come out of the square root and some things that stay under. How about this one? 25 gives us plus or minus 5. Square root of negative 1 is just I. Root 3 can't do anything, so it stays at the back. So these two parts come from right here. The 4, root 4, and the root negative 1 give me the 2I. And this 25 and this negative 1 give me the 5I in front. All right, let's see how this plays out in an entire quadratic. If I plugged in to a quadratic like this, so I'm actually giving you the plugged in numbers. So the front simplifies to 4, the back simplifies to 6. Here, this is going to become 16, and then 4 times 3 is 12, times 2 is 24. And you guys are getting pretty good at this. So underneath this square root, I've got this negative discriminant. I've got negative 8. So I'm going to go off to the side to simplify. Root 4 times root 2, but hey, don't forget about this negative 1. Root 4 gives me plus or minus 2. I now have the definition, square root of negative 1 is I. And then root 2, this whole thing goes right here where the root 8 is. So simplifying, we get 2/3 plus or minus 2I root 2 over 6. Final answer is I root 2 over 3. Notice that 2 goes into 2 once, 2 goes into 6 3 times, and that's simplified essentially to 1/3. So this is why we're learning about imaginary numbers, to see it in a full quadratic like that, so that you can keep simplifying on your result for the roots. This is 2 imaginary roots, or 2 non-real roots. Finally, what are we supposed to do with imaginary numbers last? We need to FOIL them the same way that we FOILed binomials from Unit 3. So if I give you an example like this, you're going to go first times first, outer times outer, inner times inner, last times last, and then we simplify. We just treat it like a variable. 12I squared. Now these middle terms combine. 32 plus 21. Do you see how 30 plus 20 makes 50 and 2 plus 1? So 53I combined middle term. And then here at the end, this 12I squared, don't we know that I squared equals negative 1? So our final step is to plug in a negative 1. And so we get 56 plus 53I minus 12. And then I combine like terms for a final answer here of 44 plus 53I. 56 minus 12 gives me 44. This is called a complex number because it is made up of a real part, this is the real part, and an imaginary part. Because it has these two parts with the I, we call it a complex number. Go ahead and write this one down and then pause the video and try this one on your own, foiling to see if you get it. So go ahead and pause the video and try it. Okay, let's see how you did. 2 times 5, 2 times 2i, 3i times 5, 3i times 2i. We simplify to get 10 plus 4i plus 15i plus 6i squared. Combine the middle terms to get 19i. And remember that by definition, don't we know that I squared equals -1? So our final step is that we get a -6 here. -6 plus 10 gives me 4 plus 19i. Why do I write the real part in front of the imaginary? This is called the a plus bi form of the complex number. We write it in this format.